go nuclear or something. So I love all this functional stuff, by the way. Actually, a couple of years ago, I had this talk, Flat Map and Reduce Your New Best Friends, which just looked at how functional concepts can really simplify your code. So, as Rich said, it's like good stuff. So anyway, this is on a totally different topic, microservices. And there's no code, no demos, just a bunch of slides. But sort of rather than talk about just microservices specifically, I was trying to kind of take a step back and kind of look at it from a more philosophical point of view as, like, should you use microservices? What are the trade-offs? And I found that a good way to kind of express all of those issues is in the form of a pattern or a collection of patterns known as a pattern language. So there's really two parts to this talk. One is kind of like, why should we think about patterns and pattern languages? And then there's a specific example of a pattern language for microservices, which will help you decide whether you should use microservices, and if you do, how to go about applying them. So a little bit about me before I get started. So way back, I actually did Lisp. So late 80s, early 90s, I worked for a couple of different Lisp vendors, building compilers, runtimes, garbage collectors, and that kind of thing. Eventually ended up programming in Java and wrote the book POJOs in Action, which is all about Spring and Hibernate. That came out 9 years ago, which is a long time. Awesome to see that Spring is still relevant. Right, Josh?
Well, yes.
And then back in 2007, I started tinkering around with what was then a rather obscure service called EC2. It was just sort of very much in the early days, and I think most of you know what that's all about now. And I ended up creating a startup called Cloud Foundry, which was acquired by SpringSource just before SpringSource was acquired by VMware. So there's this lovely diagram picture from the register showing fish. So this is not drawn to scale because Cloud Foundry, my company, was much more of a plankton. Otherwise, I would be fabulously wealthy now and just on an island. So I've been at VMware Pivotal, well, SpringSource VMware Pivotal for 4.5 years, and then I left about, I suppose, 20 months ago to take a break, and now I'm working on a platform for creating event-driven or reactive microservices that are based on event sourcing and CQRS. And I'm actually looking for people to kick the tires, so check out that URL. And a bunch of other links, so there's some event sourcing examples. I also created the website Microservices.io, which is a pattern language, which is where you can find this pattern language. And the whole site's intended to be a resource for helping you decide if and when and how you should use microservices. And then find me on Twitter, and also did I say try my event store? Really should. Right, so here's the agenda. It's like, why a pattern language for microservices? Why should we care about that? And then there's various different patterns within the pattern language, and I'm probably not going to go through all of them because I'm sure everybody wants to go find beer and pizza sooner rather than later. Anyway, so back in 1986, famous computer scientist Fred Brooks said that there are no silver bullets, and what he meant by that is that there's no technology that if we adopted it would give us sort of a 10x improvement in productivity. And I sort of look back over the programming languages I've used, for example, right? In the beginning it was assembler on 6502 and Z80, if anyone's familiar with that hardware. And then it was C and Pascal, and then I did Lisp, which has garbage collectors. And it's almost like anything that came after a high-level language with garbage collection is just sort of kind of minor little differences, right? There really aren't sort of massive, you don't get massive performance improvements. Lambdas are definitely good, but it's not a 10x kind of silver bullet. Which sort of explains, why Mary in the keynote yesterday said that, hardware's got 1 trillion times better, and the software really has not improved much, which is kind of interesting. But if you look at how us developers talk about technology, 30 years after Fred Brooks said there are no silver bullets, I think developers are still convinced that their favorite language, whether that is Java, JavaScript, Rails, Node.js, Go, or Rust, is the next silver bullet, right? And will argue passionately that it is the best thing ever. And often the debates sort of form like this suck-rock dichotomy where it's like, your technology sucks, mine rocks, right? And so, JavaScript, Java, Spring, Java EE. Sort of personally, I think Java EE is kind of a bit sucky. Functional, then there's the functional programming versus object-oriented programming fight going on. Like, object-oriented programming is terrible, functions of the future, and what was that?
And the past.
Yeah. Well, it's funny, right? When I was in college back in the early 80s, functional programming was hot back then. My final year project was actually implementing a functional language in Lisp, so yeah. There's a lot of passion, right? And I think a lot of, almost every technology really follows the Gartner hype curve, right? And you look around, microservices are shooting up this the hype curve towards the peak of inflated expectations. Docker is probably there already, right? And Node.js is sort of peaked and is heading on its way down, right? But it's sort of everything follows this hype curve, so it gets sort of discovered, and then there's just this massive rush to try it out and a lot of hype and so on. And then people think it's awesome, and then they realize that it's not so awesome, and it plunges down into the trough of disillusionment, right? Where, this stuff's kind of sucks, right? But then there's this whole thing where people finally understand that there are trade-offs with using a particular technology, and so you end up with it sort of reaching this plateau of enlightenment. And you just look back and everything is sort of going that way. And I think one reason why there is a lot of hype and why there is a lot of emotion is that fundamentally human beings are not rational. They're actually basically driven by their emotions. And various cognitive psychologists use this metaphor of a rider and an elephant. And so the elephant is actually your emotional self, right? And for the most part, that's actually how you decide. And interestingly, the elephant just goes where it wants, right? I mean, the rider can kind of direct it, but really the elephant gets to decide. And the rider is like our rational self. It basically rationalizes the decisions that our emotional self has made. And I think if you keep that in mind, that explains an awful lot about the world, right? Like, not only just how technology is sort of chosen, but also just go look at politics, really. None of that makes sense from a rational point of view. It really doesn't. But, we're engineers, right? And ideally we are. And we really need a better way to sort of discuss technology and think about it, that gives us a certain amount of objectivity. And I think there's a really interesting kind of sort of concept that could enable us to do that, and that's actually a pattern. Patterns have been around for a long time, right? The book Gang of Four came out in 1994, and it was this big, exciting thing. I remember, I think I was at Oopsla when you could actually touch a copy of the book. And actually patterns have sort of gone through their own hype curve. But if you look at a pattern, it's a reusable solution, right? It's something that solves a problem. But what's really interesting is that it's a problem that occurs in a particular context, right? So sort of immediately when you kind of think about a pattern, it comes with a context, the situation within which you want to solve a problem. So that always kind of narrows sort of the area of applicability for that pattern. And what's more is that patterns have a structure that end up being a great framework for discussing and thinking about technology. So if you look at that, right, I mean, there's sort of various different variations on the structure of a pattern, deciding on which, pattern book you pick up. But, I can't even remember which one I'm using, but one I'm using has, first off, patterns have a name, right? They have to have some name that describes, what they do. They have a context that captures the situation with the sort of being discussed and the context within which this particular solution applies. Then there's, of course, the problem, which is the problem that the pattern is trying to solve. And then there are forces, right? These are the issues that you have to address in order to solve the problem, and they could actually be conflicting. So you actually have to make trade-offs. And then, of course, there's the solution, right? Because that's the essence of what a pattern is. But then where it gets really interesting is that there is the resulting context, right? That there is which captures the consequences of using a particular pattern. So not only are things awesome when you apply a pattern, not only are there actually benefits, but there are also drawbacks as well. And so the pattern form forces you to actually discuss what the drawbacks are. And then also there are various issues that you have to resolve once you have applied the pattern. So it's like you solve a problem by applying a particular pattern, and then that introduces sub-problems that then have to be addressed by other patterns. And so there's sort of, you end up with this kind of set of related patterns which kind of then guide you in how to go about implementing that particular pattern. So if you look at the context in a little bit more detail, right, as I mentioned, it's got benefits. There are benefits of using this approach. Then there are the drawbacks, and then there are the issues to resolve. And the issues to resolve tend to be solved by applying other patterns. Well, there's sort of two kinds of related patterns. So there are patterns that solve problems introduced by applying this pattern, but then there are also alternative solutions as well. So it kind of ends up building up this little web of patterns that are all solving these problems within a particular domain. And the idea, you end up with this idea of a pattern language. And in fact, the whole idea of patterns themselves were kind of created by this architect, Christopher Alexander, like an actual building architect guy, who suddenly found himself famous in the software community, much to his surprise, and he even got invited to keynote at Uppsala many, many years ago. Anyway, so he wrote this book, which is like, it's a series of books, and it's like the timeless way of building. And then there's the pattern language book that's like a giant catalog of patterns that deal with architecture from the scale of deciding where to actually position a city, which tends to be best if you put a city by water because of trade, all the way down to how do you design a room. And you should have light on two sides. Rooms are much nicer if that's the case. And these patterns deal with everything in between. It's kind of an absolutely fascinating book. So, we've got patterns that force you to discuss the trade-offs involved with using them. And then you have the notion of a pattern language that forms a web of related patterns. And sort of my argument is this is a great way to talk about technology. Though, of course, I really should apply this idea to the kind of what I'm talking about, so you can kind of have this meta pattern, right? Which is, well, how do you, the problem is how do you talk about technology? And the solution, of course, is to apply the pattern format, which on the one hand has the benefit of being more objective, but on the other hand is less exciting, right? Because I shouldn't really be standing up here and saying this, such and such technology is great, because it's always, everything is a double-edged sword, which makes marketing technology a much harder job. But I think we would all be better off for it. Anyway, so that's sort of the philosophical part of the talk, and now I want to dive into the actual pattern language for microservices. So, this is still very much work in progress. It's like, I think I first wrote up two or three patterns like a year ago. I forget when exactly. And then frantically added a bunch more earlier this year because I had to give this presentation at a conference. And I really need, there's just so many more patterns to write because the microservices cover quite a broad area. But I'm trying to add more. So there's patterns in various different areas, right? So there's actually the core patterns, which is like, well, do you apply the microservice architecture, or do you use a monolithic architecture? And you can see that those patterns are connected by a dashed line. That's the notation I use to say these two patterns are alternative solutions to the same problem. And then as you can see, there's just a whole bunch of other patterns that are hanging off the microservice architecture pattern because those patterns solve problems that are introduced by using microservices. So for instance, there are deployment patterns, right? Like you've got a collection of microservices, how do you deploy them? Do you put a whole bunch of services on one virtual machine, or do you put each service within its own virtual machine or within a container? And then there's also communication patterns. Now that's important because in a monolithic architecture, the various pieces just communicate via method level, language level method calls. But a microservices system is, of course, distributed. And so you need, there's a whole bunch of machinery to support that, both an inter-process communication mechanism. There's different styles of that, right? Events versus RPC. Then there's a whole set of discovery patterns, which is like if I want to call a service, how do I find out what its host and port is? And there's various different ways of doing that with associated trade-offs. And then there's also the API gateway pattern that's basically a facade that you stick on front of your system to manage communication from the outside to the inside. So that's the pattern language, the big picture. Anything else? Yeah, so there's sort of, you've got the solid arrow that points from the motivating pattern, the pattern that introduces a problem that is then solved by the pattern that's being pointed to. And then there's this notion of sort of having a general pattern and a specific pattern, so kind of having one pattern that's a specialization of another pattern. So they form a web. So, and I'm going to talk about various bits of this until Frank tells me to stop. So first, the core patterns, right? There's two of them. One is the monolithic architecture, which is sort of the traditional way of building systems, and then there's the microservice architecture. So one of the examples I use is an online store, right? You build a system, it's got a presentation tier that's spitting out HTML. You've got various sort of modules or services that implement different functional areas of the application. So you've got a nice sort of logical architecture, at least on paper, at least in the very beginning. We've got a browser at the front, SQL database at the back. So the question is, well, how do we deploy the system? How do we kind of package up all of those services and kind of make them run? And arguably there's a number of issues that forces that you have to resolve, right? So you got a team of developers who are working away. They need to be productive. The system needs to be easy to understand and modify. You want to be able to do things like continuous deployment. You need to be able to run multiple instances of the system because for scalability and availability requirements. And you really want to use emerging technologies like modern stuff. You don't really want to be stuck with using sort of old technologies that just get increasingly painful to use. So, there's a bunch of different forces there. So obviously one strategy you can use is the monolithic architecture pattern, where you just package everything up into a single WAR file, or IR file maybe, or whatever sort of packaging mechanism is appropriate for the language and framework that you're using. On the one hand, this is great, right? Because everything about the monolithic approach is simple, more or less. Things are simple to develop. Our tools are oriented around building WAR files or jar files or whatever. It's actually remarkably simple to test. If you're using something like Spring Boot, you can write a JUnit test with a few annotations and it will start up your web application. Then you can just make HTTP requests at it to test it, or use Selenium or something. It's also simple to deploy. You just take your WAR file, copy it onto a production server, and start it up in whatever way makes sense. And it's kind of as simple to scale. You can just run multiple copies of it behind a load balancer. So at some level, the monolithic approach is super simple. Lots of examples, right, of this approach everywhere. The trouble you run into is that successful applications have a habit of growing, right? You have a team of developers who every sprint are implementing new features, which tends to translate into adding more lines of code. And if that carries on for some number of months or years, I'm not even sure the rate at which developers write code. I mean, it's sort of a bad metric anyway. But apparently, if you keep at it for long enough, you can end up with millions of lines of code, all packaged up into one WAR file. Like, I was talking with someone at another conference, and they were actually building a tool that would let them analyze the dependencies between the thousands of jar files in their system. It's like they built something. It's just like millions and millions of lines of code. And I think it was beyond their comprehension, right? And you know that once you have an app that big, you're pretty much in a world of pain, right? Like any kind of notion of agile is generally just forget about it. I mean, there are actually a couple of people, I think it's like Etsy and Facebook actually still have monoliths, if I remember correctly. Though those are the exceptions. Not entirely. Someone told me that Etsy did it that way. But most people end up in a world of pain. The system is too big. I actually even have slides for this. The system is too big to just for anyone to comprehend. It's incredibly intimidating to developers, right? And if you don't understand how it works, you can't really modify it in the right way, which tends to end up being a downward spiral, right? The design, it basically over time degenerates into a big ball of mud. It tends to be an obstacle to frequent deployments, right? Because you've got this big complex system, and in order to change one part of it, you have to redeploy the entire thing in its entirety. So, you end up having to do manual testing, big releases, and it's just horrible. It tends to overload your IDE. I have to thank Josh for this slide. It's really funny, right? Because the horse with the sumo wrestler is actually out in front, so it's clearly not slowed down. But basically, you suck in a gazillion lines of code into your IDE, it's likely to not work very well, which makes you not very productive. And then also, it tends to slow down the server or container. The larger the app, the longer it takes to start up. And talking with people, you can have application startup times of 3 minutes, 10 minutes, 30 minutes. And if that's part of your day as a developer, and is anyone in here in that situation? Anyone have painful? Don't be shy now. Yeah. But if that's part of your day as a developer, you can't go around the development cycle that many times before it's like time to go home, right? it's very, very unproductive state of affairs. Also, a monolith tends to be a big obstacle to like scaling the engineering organizations. You want to have teams that can focus on specific functional areas and work independently, but if it's all the code has to go into one release that's happening periodically, there's a lot of coordination and communication required, right? And the front-end team can say, well, I want to push my changes into production, but then they can't because the back-end team has broken the build, or everything has to be really coordinated. And then I think a massive problem is that you end up, this architecture forces you into a long-term commitment with whatever technology stack you picked at the start of the project. Because if you want to try something new, like pick some other sort of platform framework, that requires you to have a massive rewrite of your application, which is very risky, very expensive, and generally attempted. And I was talking with someone, I think, at this conference, and they were still using EJB2, right? And and that's why people, and that's sort of a modern technology. And I remember a few years ago, I was actually talking with Eric Evans from Domain-Driven Design, and he was talking about an organization whose core business application was written in the 60s in a custom, like IBM assembler dialect, and the people who wrote it were dying off, right? They were just like...
We're going through that now.
Yeah?
There's still Fortran.
Yeah. And I think we're using the latest technologies today, but they could stick, if our applications are successful, they could stick around for a while, right? But I'd argue that the monolith ends up trapping you because it's just too expensive to sort of rewrite and to use some newer technology. So I think, on the one hand, the monolithic architecture works really well until you get to a certain level of complexity or size in your application, right? For small apps, it's awesome. You can move incredibly fast. But then there's sort of this tipping point where you end up in a world of pain. And to me, I'm not even sure where the tipping point is. It all depends on the nature of the app and the level of complexity. And it's not necessarily just lines of code either. Okay, so obviously what can you do about it? Well, the solution is to use the microservice architecture. And there are various definitions of microservice, but my favorite one is this. So in this book, The Art of Scalability, I don't know if you can read that from here, which was written by some folks who worked at eBay and PayPal. They have this three-dimensional model of scalability, the scale cube. And there's sort of three axes. The x-axis is horizontal duplication, running multiple copies of your app behind a load balancer. Z-axis corresponds to sharding of your database. But the one that's really, really interesting is the y-axis scaling, which also goes by the name of functional decomposition. And that's just where you break up your app, or you break up your system into different, by area of functionality. And that to me is kind of the essence of microservices. It's not actually writing lots and lots of tiny services. It's more like functionally decomposing your app to solve the development and deployment problems that you're facing. So, concretely, with the shopping app, you build a set of services that look like this. So you've actually decomposed the various back-end services. So each one of those is a standalone service, so product info, recommendations, review, and so on. But you can also decompose the UI as well. Because a lot of sort of front-end web apps are also kind of complicated in their own right. And so functionally decomposing those, so the code that handles the checkout process can be in its own mini web app, can often make sense. And then you can actually scale these independently. So you could apply x-axis and z-axis scaling to each one of those services so that they can be sufficiently scalable and available and all of that good stuff. And I think the reality is lots of folks have been building systems this way for quite a long time. And someone, I was walking around the conference today, and someone said to me, it was like, oh, what's the big deal with microservices, right? Most people have been doing things this way for a long time. And I think there's an element of truth to that, right? Like you look at, say, Netflix, Amazon, and eBay. Each one of these companies started off in life with an application that grew. It was a monolithic application, and it grew to a certain level of scale, and it became somewhat burdensome. And they just decided to rewrite into a service-oriented architecture, which we're now calling microservices. Netflix talked about how they've got 600 different services running on EC2. Sort of a mind-boggling number just to show cartoons to children, but it's really, I still don't know how they can have 600, but never mind.
Show.
Yeah, I guess so. And a bunch of companies are talking about services in the hundreds. Amazon, another interesting example. They talk about how in order to render a page, hundreds of services are actually involved in that. Interestingly, if you go look at the product details page on Amazon, there's tons and tons of data, right, ranging from basic product info to order history. Like it will tell you bought this product 2 years ago, to reviews, seller rankings, and about 3 different forms of recommendations. And you just keep scrolling and you see more and more pieces of information. So you can imagine that operationally, there's a web app, and then when it's rendering the page, it actually is gathering all of that data by invoking a whole bunch of services. But I don't know how they get to hundreds, but anyway, it's quite interesting. And then eBay, they have some presentations that talked about how their architecture evolved, and that they have what would now be called a microservice architecture as well. So a bunch of benefits to doing that, right? Like you end up with with multiple smaller, simpler apps that are easier to understand and develop. You don't have sort of class path hell usually. And I think this approach kind of eliminates the need for OSGI, and if anyone's crazy enough to use that. And everything tends to be faster to build and deploy, right? You can organize your engineering team into small teams that focus on a particular functional area, and they're responsible for their service, the so-called two-pizza team approach. And generally, they can actually develop and deploy their changes independently of any other team. They don't have to have a big release train kind of concept. It improves fault isolation. If there's a memory leak in a module in a monolith, it's going to take down that whole process, right? Whereas if it's just if there's a memory leak in a service, it's just going to impact the availability of that particular service, which is better. And then, there's a huge topic, is arguably the microservice architecture eliminates any long-term commitment to a particular technology. If you have these services that are relatively small, well, if you're implementing new functionality, you're going to do that. You will often do that in a brand new service, and when you start, you can actually look around and just pick a brand new technology that you think is the best fit for that particular service. You're no longer obligated to use just one framework for all of your services. Now, arguably, you should have some kind of governance, because you can't have developers just randomly picking technologies, right? Though, interestingly, there's a guy in the UK, well, actually, I think he's moved to the US, Fred George, talks about developer anarchy. And he just says, personally, I can't argue too much, he just sort of says, let developers have at it, and you'll have a much more thriving, dynamic engineering culture if you do. But the key thing is you're no longer stuck with whatever legacy technology you first picked at the start of the application. And then if you're making significant changes to an existing microservice, you can just rewrite, maybe you can take advantage of that and actually rewrite it and modernize the whole application. And that's because these services can be relatively small, that's sort of relatively cheap and relatively low risk. And what's more, if whatever new technology you've picked doesn't work out, you can just go back to using the old code. It's not a massive disaster. So you kind of are much more free to just experiment and try out new technologies safely. And I think if you go look at, say, what the Guardian UK have been doing with microservices and their experience, that's actually worked out quite nicely. Obviously, there are a bunch of drawbacks. Number one, almost every aspect of a microservice architecture is like really complex. From a development point of view, right? You now have to deal with RPC. You've got to pick mechanisms and implement them and so on. Testing can be a lot more difficult because whereas before you had one system that a little annotation on your test class could spin up, now in theory if you want to do a sort of system test, there's a whole host of processes that you then have to launch as part of your test suite. And also from a development point of view, you actually have to deal with things like partial failure, right? There was a whole talk on that, excellent talk this morning from Comcast, right? So if I'm a service and I call some other service, I can be up, but the other service could be down or really slow. And so that adds a whole level of complexity to your app. The good thing is you can use a technology like Hystrix from Netflix to deal with that. What else? Oh yeah, implementing business transactions that span multiple databases without using two-phase commit can be complicated. And that's sort of why I'm working on a platform for event-driven microservices, because an event-driven architecture seems the best way to solve that problem. Plus there's just complexity of deploying the system and operating it. Where if you think in your organization it's a big enough headache to deploy one app, we'll multiply that by a factor of 100 because you've got you could easily have 100 microservices in a complex app. There's just it's complex. The good news is that almost all, basically all of this, there are solutions for, right? In terms of automation. Whether that's deployment technologies like Kubernetes or Mesos or a PaaS like Cloud Foundry. There are technologies that can actually help you with the complexity of deploying and operating a microservice system. Whereas with monoliths, they're just inherently complex and there's very little you can do to avoid that. And so for the most part, if you're building a large and/or complex application, usually microservices are the thing to use in general, though it depends. But if you do, there's a bunch of issues you have to address, right? There's issues around deployment. There's issues around how services communicate. Do you use messaging or RPC? There's issues with how clients of the system communicate with the microservices within the system. Then there's actually patterns that I haven't written yet in the area of like partitioning. Like what are the how do you actually partition the system, and so on. So that's the core. I had a lot more to talk about, but I don't know if I should or not.
You have 20 minutes.
Oh, okay, cool. We're going to 9:30.
Yeah.
Oh, okay.
If you want to.
Yeah. No, I'm really dying for that beer and pizza. No, it's good actually. I mean, well, yeah, I should get through most of this. All right. So one easy topic, right, is kind of the topic of deployment. So we've got a bunch of microservices, and it's like, well, how do we deploy them? There's various forces involved, right? So in theory, services are written using a variety of different languages, frameworks, and even framework versions, right? And each service actually consists of, you want to have multiple instances of that service at runtime because of, so you need to scale and support the load, and you need to have redundancy in your services as well. There's a need for the actual mechanism for building and deploying a service to be fast, right? You really want to be able to deploy them independently of one another and scaling them independently. Because in a way, that's like the biggest motivation for microservices, is to be able to like make a change to one service and get it into production as quickly as possible. You need isolation between all the various service instances, so that if one of them is misbehaving and consuming a lot of CPU or memory, you kind of want to prevent it from impacting other services. And you want to be able to just sort of constrain the resources. Just say, service X, you have this much CPU, this much memory to play with. And you also want a cost-effective deployment strategy as well, because ultimately, hardware, whether it's physical in your data center or virtual in the cloud, costs money, and it has to be profitable to deploy it. So there's a few patterns in this area, and there's sort of the big choice is, do you have multiple services running on a single host, where a host is a virtual or physical machine, or do you have a single service per host? So, and there are actually trade-offs. And then there are a couple of different refinements to the single service per host pattern. Sort of depends on what a host is in that context. So sort of one kind of old school way of deploying services, right? This is kind of a, back in the day when computers were like pets, you gave them cute names and you kind of kept them alive forever. So, one strategy is you've got a machine, you just run a bunch of service instances on it, right? And the services themselves could be separate processes. You could actually have multiple Tomcat instances on one host, or you could actually have one Tomcat instance and you've got multiple services running within it, or possibly maybe it's an OSGI container and you've got each service is an OSGI bundle and you've just got them all running in the same container. So there's sort of different levels of sort of density there, different options. And so on the one hand, this is quite nice because it gives you very efficient sort of resource utilization, right? You have multiple service instances sharing the overhead of certainly the machine, or virtual machine, the operating system, and so on. And they might even be sharing the same Tomcat, right? So it's minimal overhead for each service. And then in a way, the deployment is quite fast as well. You just kind of copy in the new WAR file, and maybe you hot deploy it in Tomcat or WebLogic or whatever, and it deploys. So that's quite good. But then there are some downsides, right? There's not very much isolation between the various service instances. So in the worst case, they're all running in the same Tomcat. There is basically no isolation whatsoever. It's very poor visibility as well, right? You can't actually say, well, that WAR file is consuming that much memory and that much CPU. You can't constrain resource isolation. You can have problems with dependency version conflicts as well. And who's ever doing the deployment has to be fully aware of what technology that particular service is written in. They have to know that this service requires Tomcat 6 and has to be deployed in this way. So for the most part, this is generally a bad idea. Unless, say, you're operating at incredibly high scale and there's benefits to just packing lots and lots of hopefully very stable services within the same machine. And I did hear some story about some internet company in China who were deploying their services as OSGI bundles, if I remember correctly. So there's, there might be a benefit, but there's potentially a lot of terrible downsides with this approach. So a better solution is to actually put each service instance in its own host. And the classic example of that, which is what Netflix do, is to take a service, package it up as a virtual machine image, like an AMI, and then each service instance would be a running VM, or specifically an EC2 instance. Yeah, that's what Netflix do. They have their own tool called Animator for creating AMIs. There's also Packer.io. And the nice thing about this approach, right, is you get incredibly good isolation and manageability. Each service instance is its own EC2 instance. You get detailed metrics on what resources it's consuming. It's also constrained, right? It can't exceed the resources provided by the virtual machine. And you can leverage the AWS infrastructure, auto-scaling groups, and ELVs and the like. And also, interestingly, the VM encapsulates the implementation technology. Once you package something up as an AMI, the interface is now basically start the VM, stop the VM, and whoever is doing that does not need to know that it's a Node app, a Java app, or a Rails app. So sort of the operational side is simplified. Downside, of course, is every service instance has to have the whole overhead of the virtual machine. So it's kind of lousy resource utilization, and you could argue it's quite an expensive way of deploying systems. And there's also issues around the fact that the virtual machines, the EC2 instances, only come in certain sizes, and they might not fit your service might not actually fit it exactly, and so you have a whole bunch of wasted resources in there. And also, deployment is relatively slow, right? Like the whole process of building an AMI is a relatively expensive operation, and actually booting up a machine is also a relatively slow process as well. So it's sort of, there's some downsides. So the other solution, of course, is to use Docker, right? Or some equivalent technology. And so there the idea is you take a service, you package it up as a container image, and then each service instance is a running container, which is probably running on some kind of virtual machine. Obviously the standard way of the popular thing to do is to use Docker. And then there are various Docker clustering solutions like Kubernetes, Marathon. There's also, what's it, Lattice? Lattice, yeah. So there's it's a sort of somewhat of an emerging area. There's the AWS Container service as well. So a bunch of benefits to that, right? There's pretty good isolation, right? Using kind of the container mechanism. There's good manageability. The container encapsulates whatever the implementation technology is. And you get very efficient resource utilization because it's basically you're virtualizing the OS rather than the machine, and you get super fast deployment as well. So with the app that I'm building, it takes about 5 seconds to build a container, which is basically like copying the 60 megabyte WAR file into it, not too much else. It takes about 30 seconds to push the container up into a registry that's running that's basically backed by S3. Another 25 seconds to pull the container down into the production environment. So basically it's like the build finishes, and then 1 minute and say 10 seconds later, that newly built app could actually be up and running in the production environment, which is kind of cool, really. Downside, right, is there's sort of a bunch of, you know, the infrastructure for deploying containers is fairly immature, right? It's sort of the paint hasn't dried yet. So, you know, it's like Kubernetes is getting a lot of buzz, but once you dig into it, it's a little bit complicated. And then, you know, other folks I know have actually just gone ahead and built, even recently, have just gone and built their own container clustering solution because they just didn't want to go the Kubernetes or Marathon or Mesos route. So that's a big drawback. So I might actually stop here, other than just say there's a bunch of communication patterns that you kind of have to sort of solve problems you have to address, namely around the area of like how do clients of the system, which used to just talk directly to the application that exposed, you know, just a set of endpoints, was like now there's a whole bunch of microservices that individually expose endpoints, and like, well, what does a client like a mobile app now talk to? So that's an interesting issue. And basically the answer there is to use an API gateway, which acts as sort of a single entry point into the system. And the API gateway is basically doing request routing and also API aggregation. So a request for product details might come in. The API gateway would turn around and call the catalog service, the pricing service, the shipping service, the review service, the recommendation service, to aggregate all of the data and then return a combined JSON response back to the mobile client. And then, you know, the other thing you have to think about is now you've built a distributed system, how do the services within the system communicate? So you have to make a choice, almost on an individual service basis. Does it expose a synchronous API, Thrift or REST, etc. over HTTP, or does it expose a messaging API? So you kind of have to pick the style for an individual service, pick the style of communication that it's going to use, and then also pick the actual communication technology. And then if a service needs to communicate directly with another service, right? Like, well, if you're using messaging, probably you're going to use a message broker, but there are some sort of direct service to service or broker-less solutions as well. You have to know the IP address of the service that you want to make a request to, right? And in these sort of modern cloudy environments, each service is comprised of a set of instances, which have dynamically assigned IPs and ports, and they might be auto-scale, they might be failing over and being recreated and redeployed, so that's a dynamically changing set of instances. You need a mechanism to enable a client to actually discover the available set of host and port, IP and ports that they can communicate with. So there's this whole issue of discovery as well. So you've got sort of style, we've got API gateway patterns, style patterns, and then a whole bunch of patterns around discovery. And there's sort of two big options. It's like a smart HTTP client, such as Netflix, Ribbon, or kind of having a load balance or like an ELB in between, kind of have client-side discovery versus server-side discovery. So that's pretty much my talk. Just kind of fly through this really quickly, pay attention. Whoa. Yeah, so anyway, questions? Oh, actually the summary. Yeah, so patterns, right? Good way to think about tech, discuss it, apply it. And then there's microservice pattern language is a good way to think about, discuss, and apply microservices. So thank you, and you can find me here.
We have time for one question.
Yeah.
So just a quick question. The context is, so now you have the operation where you have a lot of microservices, and presumably they are owned by separate teams. Presumably they're talking XML with JSON with each other. So what is your take on having each team and each microservice communicate to the other over raw REST and WebSocket versus providing a jar file where you have some domain object and kind of the client connectivity hidden within that. So it's basically fat jars versus raw.
Well, yeah. So you can say that a team could provide a client library.
Yeah.
That can be helpful. I mean, it depends on sort of how polyglot the environment is, right? Because it will be somewhat of a burden on a team to have to provide a library in 5 different languages, for instance. But I don't really see any issues with that. But it's like ultimately it has to be.
Presumably, I think the drawback is that once you no longer control the monolithic service and all the domain objects are kind of across each microservice, everyone who's calling it will have to convert it and understand what the objects are versus you providing a way to actually have a static way of, hey, this is a product, this is the price, this is whatever. So giving a more refined way to figure out what it is rather than each service.
See, I mean, I guess I just think of the client library as just being a shallow wrapper on top of whatever API they're providing anyway.